Okay, so welcome back, everybody. Sorry about that. A little delay in getting things running, but we're good now. Seems everything's fine. So last time uh, we ended with statement of Green's theorem, and we did one example of Green's theorem. So here's one, or here's rather the statement of Green's theorem to remind you. See, could you possibly do a problem similar to number 6 on the MATLAB? I can't find anything like it. I have to remember what number 6 on the MATLAB even is. What did I say? Uh, um, Let me look at the, actually look at the MATLAB project. Um, oh, well, um, so, that is so I mean doing that line integral in number 6, the top half of that circle, this is that circular curve in space. So you can parameterize that. I mean, there's a number of ways you can parameterize that, but you can pick how you want to parameterize that if you like. Like if you were doing this by hand, number 6. This is number 6 in the MATLAB. If you were doing this by hand, then you could parameterize that it's a circle in the YZ plane. So you could parameterize that circle. You want it oriented clockwise, so that should be evident in your parameterization. And then you compute it like you compute any other line integral. So I may do an example like that. Maybe after we finish our discussion of surface integrals and we finish these named theorems, then I'm gonna finish early. So what I'll do is I'll go back and do a review on a bunch of stuff, and maybe I'll do some examples of like brute force line integrals. You're also going to do brute force line integrals as part of your last homework assignment, which I'll assign over the weekend. So you will have more practice with this stuff. Okay, so Green's theorem. Here it is. So I have a simple region in the plane. So this applies to a line integral that's two-dimensional. So a line integral on the plane. So let its boundary curve C be a piecewise smooth curve oriented counterclockwise. Let M and N be functions that make up this two-dimensional vector field. And so the line integral of this vector field, using this notation that I introduced a couple lectures ago, is, or can be computed as a double integral of this thing, right? This weird expression underneath the integral here. And so I'll talk a little bit more about this in a second, but what's really going on here is that you're swapping back and forth between an integral along a boundary of something and an integral along the thing that the boundary encloses, right, of something else that's related to this thing. Okay. So you don't realize it yet, but you've actually seen something like this before. In fact, you've been doing this the entire time you've been doing calculus. It just doesn't look like it. Okay. So I will talk more about that in a second. But I wanted to do another example of using Green's theorem. So let's pick one right out of the book. So let's see here. Yeah, here's a good one. So let C be the closed curve below. Okay, and let's say oriented counterclockwise. I'll indicate that in the picture. So evaluate the line integral over this curve C that I'm about to draw of 2 y cubed dx plus x to the fourth plus 6y squared x dy. Okay. All right, so what is the closed curve C that I'm referring to? So here's my xy plane. So consider the curve C and the region R that it bounds to be as follows. So the origin here, here's 1. Here is 1 on the y-axis. So consider the curve that goes along the x-axis from 0 to 1. And then it goes like this, following the curve, which is, it's not the greatest drawing. This is x to the fourth plus y to the fourth is equal to 1. Okay, so it goes like this till it hits the y-axis at 1, and then it goes down from 1 to 0 along the y-axis. Okay, so of course this curve encloses a region R. Okay, but here's my curve C. This curve C is the boundary of this region R that I've drawn here. Okay. So, what would I have to do if I was going to compute this line integral without using some kind of trick? Okay. So, without using some kind of trick, I would have to come up with a parameterization for this curve. Okay, so first of all, this is a piecewise smooth curve. It has corners here, right? So I would parameterize this linear piece, and then I would have to parameterize this piece. This is a graph of a function, so it's easy to parameterize. So parameterizing this linear piece is not hard. Parameterizing this piece that's a graph of a function is also not hard. And parameterizing this last linear piece is also not hard. But I would still have to break the curve into these 3 pieces. And then I would need to plug that parameterization into the vector field and this line integral here. I would have to compute dx dt, dy dt in each case, which wouldn't be that bad for the linear pieces. It'd just be constants. And then for this curve piece, it wouldn't be that bad. You compute it directly from this thing. But that's still 3 line integrals that I would have to do separately and then sum the results, right? So this would turn out to be a really, really nasty problem. But with Green's theorem, I can do this in one go. And I can do this with one go as a double integral over this region R that this curve encloses. Okay. And so then recall how Green's theorem goes. So Green's theorem tells me that I can do this by simply noticing, oh, well, this is my M, okay, and this is my N. And so Green's theorem says that this is a closed curve. It's piecewise smooth. It's oriented counterclockwise. Okay, M and N are functions that are nice and continuous. They're actually smooth. They have infinitely many derivatives, so even better. And so this is equal to, by Green's theorem, the double integral over this region R, that I'll have to describe here in a second, of the x partial of N minus the y partial of M, right, dA. Okay, so I need to compute this thing. Well, I'm also going to have to describe R here, right? But R's not that hard to describe. It's a vertically simple region, Right, how do I describe my region? All right. So as a vertically simple region, I have y between what and what? Well, between the constant function 0. This upper function, I can just solve for y here, right? This is just the fourth root of 1 minus x to the fourth. All right, so the y is bounded below by constant function 0, bounded above by the fourth root of 1 minus x to the fourth. Right, just directly from this. And x goes from 0 to 1. Okay. All right, so here's my region R, described as vertically simple. Now I need to compute the x partial of n. What is the x partial of n? So here's n here. So I take the x partial of this thing. This is 4x cubed plus 6y squared x. The x partial of that is just 6y squared. So the x partial of n is 4x cubed plus 6y squared. The y partial of m is 6y squared. Oh. Okay. That's not too bad. Right? It's not too bad at all, because the x partial of n, I subtract from that the y partial of m, and so these things are going to cancel. I'm just going to be left with 4x cubed. Right? And so, let's rewrite this. So I have the line integral over my curve C, described like that, of 2y cubed dx plus x to the fourth plus 6y squared x dy is by Green's theorem. So that's, this equality is Green's theorem. It is the double integral over R of the x partial of n being this second component function in the vector field, minus the y partial of m, that's my first component function, dA. So using this characterization of R is vertically simple. This is the integral from 0 to 1, the integral from 0 to the fourth root of 1 minus x to the fourth. The x partial of n was 4 x cubed plus 6y squared minus 6y squared dy dx. And so this is the integral from 0 to 1, the integral from 0 to the fourth root of 1 minus x to the fourth. 4x cubed plus 6y squared minus 6y squared, the 6y squareds cancel, and so I'm left with 4x cubed dy dx. Okay. So the integral that I am doing first is with respect to y. So I'm treating 4x cubed as a constant. So this is the integral from 0 to 1 of 4x cubed y evaluated from 0 to the fourth root of 1 minus x to the fourth dx. Evaluating at 0, I get 0. And so I get the integral from 0 to 1 of 4x cubed times 1 minus x to the fourth to the 1/4 dx. Hey, I have exactly my du that I need in order to do this integral as substitution. Right? Well, I need to adjust a little bit, but still, this is the term that I need, right? I need that x cubed term here. Okay, and so the idea is I'm going to want to use the substitution u is equal to 1 minus x to the fourth here. So if I do that, then I need minus 4x cubed. So I have 4x cubed here, so I'm going to have to introduce a minus sign here. But when I do that, I'm doing really the integral of u to the 1/4 du. And what is the integral of that? Well, it's u to the 1/4 plus 1, so it's u to the 5/4, right, over 5/4. So so then what do I get here? So this would be, so this 4 is actually included right, in the du here. So I'm going to introduce a minus minus here, and what I get is minus 1 over 5/4 times 1 minus x to the 4th to the 5/4 evaluated from 0 to 1. So this is minus 4/5 evaluated from 0 to 1 here. So at 0 it's 1, and at 1 it is 0. Because I'm evaluating from 0 to 1, this is going to be minus 4/5 times 0 minus 1. So this is 4/5. Okay. So there's another example of how to use Green's theorem to make your life easy in this way. Okay. So when I wrote Green's theorem down, I used this to say that this should kind of tell you how nasty you can expect a line integral to be, kind of heuristically, because Green's theorem is a nice fact. It's a fact that doesn't always apply to line integrals, right? So the curve itself needs to close up over a region, right? So for instance here, right, my curve needed to enclose a region, and it needs to enclose a region because Green's theorem doesn't make sense otherwise. Right, so here's a statement of Green's theorem. If there's no region that gets enclosed, so if my curve is just open, it just has two, or I shouldn't say open. If my curve is open in the sense that, it doesn't close up, it just has two, different endpoints and doesn't actually enclose a region, then I can't use Green's theorem, right? Green's theorem doesn't even make sense because I need to do this double integral over some region that's enclosed by some boundary curve C. Okay, so this is a special thing. Okay, and what this should tell you is that, even in the nicest kind of scenario, basically, you can see that a line integral in the plane is some double integral here. Okay, and so even in a nice case, it's basically at least as bad as a double integral of some kind. And so yes, while you can pick particular line integrals that are, you could do in 20 seconds, in general, a line integral is going to be at least as bad as a double integral. Okay, and typically it's going to be way worse than that. Okay. All right, so let's use Green's theorem to go back. Now that we have this this characterization of so let me just write the statement of Green's theorem again because it's nice to have it out here like this. So if we are computing a line integral like this under those same assumptions, so C is a closed curve that encloses a region, it's oriented counterclockwise, encloses some region R in the plane, then Green's theorem says we can compute that line integral as double integral over that region of the x partial of the y slot function minus the y partial of the x slot function, right, dA. So that's the quick and dirty of Green's theorem. All right, so let's apply this to what we have already done with double integrals. So in particular, recall that the area of R could be computed in another way, right? So the area of R could be computed as a double integral. It could be computed as the double integral over R of 1 dA, right? And we saw that if we actually worked this out, this was just the same way of computing the area, say, between two curves that we did in Calc 1, right? So if R is a vertically simple region, then this basically just boiled down to the area between two curves, like you would have seen in Calc 1. Okay, so since the area of R could be computed like this, if we choose, if we choose a vector field, that's a weird we. Here, let me rewrite that. That looks weird. Here, if we choose a vector field that has m and n such that, so if we choose m and n such that the x partial of n minus the y partial of m is equal to 1, then by Green's theorem, under the other assumptions, right, of Green's theorem, so it's not just enough to choose this, but under the other assumptions of Green's theorem, the integral, the line integral over c of m dx plus n dy is equal to the area of R. Okay. And so the main thing we need for this to be true is to choose a vector field that satisfies this. Okay, so do you see why that is? Well, if the area of R is computed as double integral over R of 1 dA, if the x partial of m minus y partial of m is 1, then by Green's theorem, I replace this underneath the double integral with 1, and that's just the area of R. Okay, so this is kind of a little neat fact. So to see an example of this, of course, there's many ways that we could do this. So there's a number of ways to do this. In fact, I'll list out some of them here. So what are some ways to pick m and n such that this is true? You could do the really easy thing. You could say, so here's one way of doing it. What if I pick m equal to 0 and n is equal to x? All right, will that do it? Well, the x partial of n is 1 minus the y partial of m is 0. So this is 1 minus 0, which is 1. So yeah, that works. What's another way of doing it? Well, I could let m be minus y, and I could let n be 0. All right, so if m is equal to minus y and n is equal to 0, then the x partial of n is 0. The y partial of m is minus 1, so this is minus minus 1, which is 1, and that works. Okay, what about something where they're not both, or where one of them's not 0, right? So both of them are something non-zero. Well, I could let m be minus 1/2 y, and I could let n be 1/2 x. That also works. So to see that it works, the x partial of n is 1/2. The y partial of m is minus 1/2. So this would be 1/2 minus minus 1/2. That would also be 1. Okay. And so, rewriting this in line integral form, so the area of R is, or can be thought of by Green's theorem as being the line integral over C, where C is the boundary curve. Here, maybe I'll write that. All right, C is the boundary curve, oriented counterclockwise. So this is the line integral over C of x dy. That's also the same as minus the line integral over C of y dx, or 1/2 times the line integral over C of x dy minus y dx. So this is me computing area of region. All right, so here's R. And this is just a number of ways of computing the area of a region by integrating these particular vector fields that I cooked up over the boundary curve. Okay, so this is an example of a line integral computing an area. Okay. So this might be a little bit weird because you tend to think of, I mean, a curve, right, is a one-dimensional thing. And our one kind of example of an application of a line integral was if we thought of, for instance, if we thought of like a curve being a wire that's like situated in space. So the curve itself is like the how the wire is situated. So if you think of taking a wire and like, you know, kind of jiggling it around in space and then sitting it in whatever position it ends up in, as long as it doesn't have any sharp corners or anything. Well, even if it does, it's not a problem. But think of that wire sitting in space as being, you know, the curve. If that was the case, right, if we had the mass density function along the wire describing, you know, the mass density distribution along the wire, if we did the line integral of that function along that curve, that gave us the mass of the wire. Okay. And then our example of vector field is very similar. I mean, the example of the vector field that we used was the work done by, say, by a force represented by the vector field pushing a particle along the curve. Okay. So then here, this is us computing an area by a line integral. So maybe this seems a little bit weirder, or like this is a different sort of computation, or like the dimension is wrong in some way. But this is just showing you that this is another interpretation of a line integral, and it is computing an area in this case. This is kind of foreshadowing what we are going to talk about next. Okay. And so the next thing that we really want to talk about here is basically the next big named theorem, which is Stokes' theorem. But before I do that, I have to talk about surface integrals. And we've already done most of the background in talking about surface integrals, so that's nice. We'll basically be able to quickly bring you up to speed on that. But even before I talk about the specifics of surface integrals, I want to mention a couple of things. And one is a big question. What is it that's going on in Green's theorem? Okay, what is it that's going on in Green's theorem? So, the answer is we are seeing an example of a special case of a very deep and complex theorem. So before, when I mentioned this, I called this Mega-Stokes theorem. It's actually called Stokes' theorem, but the reason I'm calling it Mega-Stokes theorem is that we are going to have another theorem called Stokes' theorem, and I don't want you to be confused. So as I said before, what we call Stokes' theorem in this class is just a special case of a much more general theorem called Stokes' theorem. And the reason it's called Stokes' theorem is just because of, so I mean, historically, the original Stokes that proved Stokes' theorem did not prove it in the form that it is known as Stokes' theorem. But it was, again, a special case. The special case we're going to talk about here in a little bit. But what is the Mega-Stokes theorem? So what does this say? I'm not going to state this exactly as it appears because it wouldn't make any sense. But I'm going to soften it a little bit. And so the idea, okay, the idea in Mega-Stokes theorem is that you have a region. Okay, so you have a region, and Maybe your region is 2-dimensional. Maybe it's 3-dimensional. Maybe it's 17-dimensional. Okay. But you have a region, we'll call it omega. Okay. And it turns out that this region omega really can live in any dimensional space, so we'll say that it's n-dimensional. Okay. So if your omega lives in Rn, it is this n-dimensional object. Okay. Well, the boundary of omega lives where? Right? If your object is n-dimensional, the boundary of your object has one less dimension. Right? Okay, and so we can just quickly go through this. All right, so for instance, right, if I have a one-dimensional, so if here's omega, here's examples of omega. So if I have a one-dimensional thing, say an interval, or a curve, but we're just going to take an interval, what does the boundary of omega look like? So what's the boundary of this little line segment? Well, those two disconnected points. Now, because they're disconnected, we have to think of a way of kind of bringing them together or connecting them in some way. All right, so I'll mention that in a bit. But this thing is one-dimensional, right? So this is 1D. It's a one-dimensional line segment. But its boundary is zero-dimensional. It's just 2 points. So it's 0D. Okay. If your omega is 2-dimensional, so let's say it is, a circular disk. Well, that's 2D. What's the boundary of that circular disk? The circle, which is 1D. If your omega is, say, 3-dimensional, so it is a 3-dimensional ball, right? I'm not going to fill that in or it wouldn't make any sense. We'll say this is a 3-dimensional ball. What's the boundary of that 3-dimensional ball? Well, it's just the sphere, so maybe I will fill it in to indicate that it is full. So this is a full ball, that is the sphere and everything inside of it. And it can be kind of hard to see the equator there. Okay, but what is the boundary of that thing? Well, it's just the sphere, right? The boundary sphere of that 3-dimensional region. And that's 2D. Right? A sphere is a 2-dimensional object. Okay, it's a surface. Surfaces are 2-dimensional. And of course, if omega is 4-dimensional, then its boundary is a 3-dimensional object. Okay. So since we live in 3 dimensions, we can see the boundary of 4-dimensional objects, but we can't see 4-dimensional objects themselves, right? It's a little bit too hard for us to visualize. Okay, and so on. All right, now why did I go through all of this? What is the idea? What does Megastokes' theorem say? So what Megastokes says is the following. Okay. If I want to integrate if I want to integrate along some region omega, something that I will call del f, right? Then in order to do that, I can integrate along the boundary of omega, the object f. So if you like, we're abusing notation here, we have this boundary operator del. Okay, so this boundary operator can be applied to big F. This big F, the reason I'm being vague here is that that big F could be a function. It could be a vector field. It's some object that we want to integrate. Okay, and we want to integrate it along the region omega. But as I previously said, omega is just some region that lives in Rn, right? And so if omega is one-dimensional, well, if omega is an interval, this is not too bad. If omega is a curve, if it's still one-dimensional but it's a curve, this is a line integral. Okay, if omega is a two-dimensional region, say in the plane, then this is a double integral. And maybe we'll go through those piece by piece. So let's look at special cases. Let's go all the way back to Calc 1. Let's say that omega is an interval, a to b. Well, in this case, right, I'm going to be integrating over an interval from a to b. Well, I know exactly what that is. Okay, so if omega is the interval a to b, let's take f to just be a function. And so let's take del f to be the derivative of a function. So it is the derivative of my function with respect to some variable. Okay. As we saw before, what is the boundary of omega in this case? It's these 2 points, A and B, that are disconnected. Now, how I want to interpret this, or an integral along this, we'll see in a second. And so, what is this? This is the integral from a to b. So the integral over omega of del f is the integral from a to b of del f here is df dx with respect to x. What is this? You should know this from Calc 1. How do I do this? This is simply big F of b minus big F of a. But in Calc 1, you had another way of writing this. Another way of writing this, as we've written it several times in this course, is big F of x evaluated from a to b. What is this symbol? What does evaluated from a to b mean, right? That's in quotes, because what does that mean? Well, it means exactly this thing. You plug in the top endpoint, b, and subtract from this quantity, plugging in the bottom endpoint, a. That's the evaluation from a to b. That's how we define this in Calc 1. Okay, what is this? This is, in quotes, the integral over this zero-dimensional set, the boundary of AB, of F. This thing that we're doing here is we consider, instead of just these 2 points sitting apart, we consider the signed difference of 2 points to be the correct boundary operator. And so what is the thing here in this case? In the case that omega is an interval, AB, this thing is what? What is this thing that I've written out? The integral from a to b of df dx is f of b minus f of a. What is that? All right, that's literally this thing that I wrote out. That's my Megastokes theorem, but it's my Megastokes theorem applied to the special case that omega is the interval from a to b. What is this? This is the fundamental theorem of calculus, right? Or one of them. Okay, this is FTC. And so the fundamental theorem of calculus is already one of these things. Okay. All right. What about the case that omega is a curve C like this? All right, so here's my point. We'll call this A, call this point B. So omega is still one-dimensional. We still have signed difference of points here, but now they're not points along an interval, they're points A and B like this. And what if we take our del F, right, to be the gradient of F? Right. What is the integral along omega? Right, so this is the thing we're trying to look at. We're looking at the integral along omega of del F. Okay. But then an integral on omega is an integral along a curve. It's a line integral. Right? So this is the integral along a curve of del F here. I'm calling the gradient of F. Right? And so what is this? This is, by fundamental theorem of line integrals, this is f of b minus f of a, right? Which is the thing that we're calling the integral over the boundary del omega, right, of f. Again, signed difference of points is the boundary operator here. So integrating along the boundary, which is the integral of, along 2 points, is this signed difference of points here. What did I just write here? Right, what is this thing? Here is the meat of it, right here. What is that? This is just a restatement of the fundamental theorem of line integrals. Okay. Let's keep going. What if omega is a two-dimensional region R that looks like this? This closed 2D region R. In that case, del omega is the curve C, that is the boundary curve that looks like this. We'll say it's going counterclockwise. All right, so this is del R. So trying to apply Megastokes then, my integral over omega of f is equal, of del f. Well, what is del f here? Well, here I'm going to let del f be, if f is mi plus nj, right? Then del f is going to be the x partial of n minus the y partial of n. Okay. And so my integral on omega of del f is going to be, what is an integral along omega, which is a two-dimensional set, right, in the plane? Well, what is an integral along a two-dimensional set in the plane? We had a name for that. It's a double integral, right? It's the double integral over R of del f, which is n sub x minus m sub y dA. You already know what's coming now. This is the integral, or the line integral over c of m dx plus n dy, which of course I can think of as the integral on the boundary of omega of f, right? Well, what is this? This is Green's theorem. Okay. And so we're going to have two separate named theorems that are going to follow, okay, later, that are going to just be new examples of this. All right, so what does this tell you? Every single one of these things that I wrote out, so fundamental theorem of calculus all the way back in Calc 1, fundamental theorem of line integrals that we just saw a couple lectures ago, Green's theorem, what we're going to call Stokes' theorem, and the divergence theorem, are all examples, they're all special cases of a single theorem that I'm calling Mega-Stokes theorem. That is this statement that the integral over region of thing that I'm calling del f, okay, where we saw that this interpretation changes depending on the context. Sometimes it's the derivative, sometimes it's the gradient, sometimes it is this weird thing showing up in Green's theorem. Okay, the f, sometimes it's a function, sometimes it's a vector field, right? And omega is changing dimension, right? Sometimes it is an interval, sometimes it's a curve, sometimes it's a 2D region in space, sometimes it's a surface in space, sometimes it's a 3D region, okay, in space. All right. And the integral over omega of del f is the integral over the boundary of f. Okay, and like I said, with abuse of notation, you can think of it as telling you how you can move this del operator from underneath the integral to being the boundary operator on omega. Okay. So you're going to get two more examples of that, but that's what's going on. And so another kind of simple way to describe this is we are doing the fundamental theorem of calculus in many dimensions, in many different contexts, all at the same time. Okay. So I need to talk about surface integrals before we can do much else here. Okay, so I only have a couple more minutes left. So what I will say is we already talked about the notion of integrating over. So integrating over a 2D region in the plane. So we spent a lot of time doing that, right? So here is my 2D region in the plane. Okay. Integrating over this region is the notion of doing a double integral over R of some function, f of x, y, dA, right? This was the notion of a double integral. Was my notion of integrating over a 2D region in the plane. Okay. Now, what if, right, just in the same way that I had the notion of integrating over a 1D interval, right? So if this was the integral from a to b, integrating over that is the integral from a to b of f. Right, f of x dx, we'll say. All right, but if I took this and I shook it up a little bit, then what I got was integrating over a thing that looked like this, right, which was our motivation for talking about line integrals, right? And of course, if the thing that I'm integrating was the line integral, or over the line or the curve itself was a vector field, then this would be, line integral, right, of f dot dr was the notation we used. Okay, so I want to do the same thing here. So I already understand the notion of integrating over a 2D region in the plane, but what if I take that 2D region and I shake it up? So I think of taking a rug, right? And instead of leaving the rug flat on the floor, I introduce rumples. I, rough it up so that there's waves to it, right? So the region, I take this region, I shake it up like that in space, and so what I end up getting is something like this, okay, which is a surface, right, that we have been working with since chapter 13. So I get this surface sigma, okay, which is a surface. It's a two-dimensional thing. Okay, you could think of it as sitting in space, but you don't have to right now. This is just some flat 2D thing that I have ruffled up, okay, in some way. I want to talk about the notion of integrating over a surface. Okay. So then the notion of integrating over a surface is going to be this thing. I'm going to use double integral notation, but I'm going to be integrating over some surface sigma rather than some 2D region in the plane of something. Okay. D big S, we'll say. Okay. This is the notion of a surface integral. Okay. Just like our notion of integrating over a curve was a line integral, integrating over a surface is going to be a surface integral. So, when I keep saying that we've already done a huge amount of the work in defining surface integrals, what do I mean? How did we define line integrals? Right? So a line integral over a curve C, some vector field, what was required? I needed a parameterization R of the curve C. Once I had that, I computed dr dt, like we did, all the way back in chapter 12. I plugged the parameterization into my vector field F, and then I dotted the parameterization plugged in with dr dt, and I got some scalar valued function of my parameter t, and then I integrated that thing. But the integral I did, of course, was a Calc 1 integral, an integral of just a single variable. Okay. So then how's a surface integral going to be defined? I'm not going to write it out here because we don't have time, but what I'm going to say is it's the same thing, except now I'm dealing with a surface rather than a curve, but we have already talked about how to parameterize surfaces. So I parameterize surface. I have some R of uv. That's my surface parameterization. If I'm integrating, say, a vector field over a surface, okay, what is it that I'm doing? I would plug that parameterization into my vector field. Okay, I would then do something else with it, which we'll talk about. Okay, I will do something. I will dot it with something, right? So I will dot it with some equivalent thing to dr dt. Maybe to get some scalar valued thing in two parameters, and then I will double integrate that. Okay. So that is exactly how surface integration goes, and we're going to talk about it starting right from the top of the lecture next time. Okay. So on Monday, we'll do surface integrals and Stokes' theorem. We will probably finish that discussion by in the first 10 minutes of class by Wednesday. We'll do the divergence theorem, and after that, it's going to be a lot of review, basically, because we're going to have a couple days extra where the material's finished, and we'll just have some review sessions. You all can just ask me what any kind of remaining questions you might have. So anyway, I will see you all then. See you all on Monday.